you react to that commercial? You realize you guys have like off the girl and the glasses she had. Were you serious? Yeah, I'll never buy that girl. Those glasses ugly. Never go with my $100 jackets and maybe $80 jeans I wear.
Are you very excited about Friday?
Are you excited about Friday?
Excited you're not just like have 10 minutes of class you might say.
Well, I still have 2 more classes left. If it were the last one, I would have probably considered your thought.
Alright. Let's act like it's the last one.
Just cancel the rest of the classes.
Yeah, it just practice for your last one.
You guys have any questions from what we did last time? So we began probability, and remember we began with the naive definition of probability, but the naive definition isn't enough, because we saw that there are 2 assumptions in the naive definition, and there are there are places where those assumptions wouldn't hold. Also, we looked at some paradoxical types of problems where we saw that answering probability questions could be tricky. Sometimes the answers seemed incorrect even when they were correct. Like the birthday paradox, we saw that some of one of the answers was a little bit surprising. So what it means is that we need to think about how we are going to develop the theory of probability. And so so what I want to look at today, first thing that I want to think about is, okay, I need a definition of probability, first of all. So the naive definition doesn't work in general, so can I come up with a better definition? So before I go there, in everyday life, when we talk about probability, right, we use the subjective definition of probability. So the subjective is basically, it measures the degree of one's belief. For example, it is 90% probable that Shakespeare actually wrote Hamlet. The probability that Zach Goodchild will pass his actuary exam is 95%. Okay. Zach Goodchild was a student in my probability class, math 4651, a couple of semesters back. So there is another view of probability which is empirical and uses relative frequency. So and this is the definition of probability that might be intuitively very satisfying to you. So what it is that given an event A, define the probability of A to be the relative frequency of A in a long series of repetitions. Okay. So for an event A, take the probability of A to be the relative frequency of A in a long series of repetitions. In other words, the probability of A is the proportion of times A occurs in a long series of repetitions of the underlying trials. So let me be a little bit more precise. Let n of A be the number of times A occurs in the first n repetitions of the associated experiment. So n of A is the number of times A occurs in the first n repetitions of the associated experiment. Then P of A is defined to be the limit as n goes to infinity of n of A divided by n. Okay, so n of A over n is what? N of A over n is the proportion of times A occurs in n repetitions of the underlying trials. Is everybody clear what this definition is saying? So this is where we are saying the probability of A is the relative frequency of A. So this is a very intuitively very satisfying definition, right? You know, basically it's saying, suppose you have a fair coin, right? Let's say the probability of getting a head is half. So basically what you're saying is that you keep tossing the coins many times, and you look at the number of times you get a head. So divide the number of times you get a head by the total number of flips, and that's the probability of getting a head. Is that making sense? So intuitively this is a very satisfying definition. However, there are some problems with it. You know, when you toss a coin, right? So if you want to use this as a definition, right, of the probability of an event, the problem is then you have to assume that this limit exists, and not only that this limit exists. You know, each time you flip, if you go back to the flipping a coin example, right? As you flip coins, you get a sequence of heads and tails, right? Now, if I let one of you flip the coin, you're going to get a sequence of heads and tails. If I ask someone else to flip the coins, he's going to get a sequence of heads and tails, right? There is no reason to believe that you're going to get the same sequence, right? You're probably going to get different sequences, right? Different sequences of heads and tails, right? So if you are using this definition, you have to assume that for any sequence of results, right, this limit must exist and be the same number. Okay, and that's a really that's an assumption that seems to be a little bit too strong, and also it is hard to work with. So even though it is intuitively very satisfying, this isn't going to be the definition that we take on. Okay. And once again, if you are tossing a coin, let's say the probability of getting a head is 1/3, then we think of 1/3 as the proportion of times the H occurs in a long series of tosses. So even though the relative frequency definition here of the probability of an event is very satisfying, as we said, there are some disadvantages with it. Again, also, besides what I have already said, there is also the problem that you can't carry out the experiment many times in practice. And the question is, even if you take the limit definition of the probability of A, the question is how big n do you need to pick to get a good approximation of the probability of A? Okay? And that's not also clear. Is everybody okay with that? If you guys are writing this down, let me know when you're done writing it down. Okay, so should we start with the following assumption that the limit as n goes to infinity of n of A over n is constant for any possible sequences, for any possible sequence of repetitions? Well, we just said probably not. However, not clear why this needs to be true. So most people agree that we should start with simpler, more self-evident axioms. So one thing we could do is we can start with the axiom that the limit as n goes to infinity of p of A over n, n of A over n is a constant no matter what sequence of results you have, but like I said, that's hard to work with. So most people agrees to start with simpler, more self-evident axioms, and this Kolmogorov's axioms. Kolmogorov is a Russian mathematician, and he came up with some very simple self-evident axioms in 1933, and then we used those axioms to develop the theory of probability. So the idea is that let's use so axioms are what? Axioms are certain statements that we say that they hold true. We assume those are assumptions we make. Okay, and then we develop the theory based on those assumptions. And what you're going to see is that the axioms or assumptions that we make are very simple, that all of you will agree that those assumptions should be true about probability. Okay? So let's see what they are.